All right, so this is calculus. We are looking at the second day of the second part of the second lesson in chapter 5. So lots of seconds on this one. All right, so last class what we did was we went through and we were calculating what the area would be if we were to find a bunch of rectangles and sum them all together. So continuing on with that, whenever you do these things, we saw yesterday that there were rectangles that sat inside the curve and left extra space, and then there were ones that sat outside the curve and actually created an area that was larger than the actual area. So on these, whenever you're dealing with rectangles that are inside of the curve, those things are called inscribed rectangles, because they sit on the inside. Whenever you've got your rectangles and they're sitting on the outside of the curve, those things are called circumscribed rectangles. So you might remember these words back from geometry. Inscribed is when it's on the inside, and then circumscribed is whenever something's on the outside, like a circumscribed circle or rectangle, things like that. All right, so whenever we are doing these and we start adding in all of these areas of these rectangles, whenever you find the sum of the inscribed rectangles, that's going to be called a lower sum. And the formula to find this lower sum, we're going to denote it by a lowercase s of n, and that's going to equal the summation from I equals 1 to n of f evaluated at a lowercase m sub I times delta x. And here in a second, we're going to talk about what all these different pieces of that formula mean and where they come from. And then for the next part here, whenever we're looking at the sum of the circumscribed rectangles, those then are the ones that are on the outside. That's going to give us the upper sum. And the formula then for the upper sum is going to be a capital S of n equals the summation from I equals 1 to n of f evaluated at a capital M sub I times delta x. So what this means then and what we're talking about, if we go over off to the side, I'm going to draw myself a quick little curve here. So here is my XY axis. I'm looking at the positive X, positive Y, so first quadrant here. Draw yourself in just some sort of curve that we're going to be looking at. And first off, whenever we start talking about that delta x, what that delta x is going to be is it's in the same place on our formula that we had yesterday when we were talking about width. So it's going to be the width of all of our rectangles. Well, if we are looking from point A to point B, and we're wanting to find the area underneath the curve here by drawing in our rectangles, the width of each rectangle is going to be dependent upon how many rectangles I put in. So whenever we were doing the ones yesterday, we had to put in 5 rectangles. The distance between my 2 points was 2, so we took 2 divided by the 5, and each rectangle had a width of 2/5. So what you're going to do is first you figure out the distance between these points, and then you go and you divide it by however many rectangles you have. So our delta x is going to be the difference between the points, so b minus a, over the number of rectangles in. So that's the first part here. Then for our big M sub I and our small m sub I, if we were to go ahead and come in here and draw in a rectangle, first I know that I could come in here and make a point, come across whatever my width is, and then back down again here. If I have this part here and it creates then a circumscribed rectangle, which is the ones here on the outside, this distance here that I'm at that gives me the height of that rectangle, that is my f of capital M sub I. So that means that this x value here would be that capital M sub I. It's the y evaluated, or the function evaluated at the x value, that creates that large rectangle. Whereas if we come in on the inside and do our inscribed rectangle here, so we make this little one, then whatever this height is at, that's going to then be our f of little m sub I, which means that this x value is this little m sub I. So with these then, all this is it's showing that we're evaluating then the function, kind of like whenever we were plugging in the 2/5 and we moved along to catch all of these increments of 2/5. That allows us to move along and catch all of the increments with our rectangles that we have underneath the curve. Now, the other thing too I want to point out with this is that whenever we are figuring these things, when we did them on the example last class, we started at 0. And the thing is that you're not always going to start at 0. Like this one, we actually were starting our rectangles at this value of A and running out to this value here of B. So whenever you guys are figuring these things and it doesn't just simply start at 0, what you're going to want to do is, in order to find our, let's see, let's do it by right and left. So if I want to find my right endpoint, so we'll put here our right endpoints. And the reason I say right as opposed to the small m or the large m is sometimes the right endpoint is actually going to give you a larger rectangle, because with the way this curve is, if I'd have gone here at B and gone up, it would have given me my capital M sub I, whereas here on this one, it's giving me the lower. So it all depends on what your curve's looking like. So we're just going to refer to it as a right and a left, and then we'll look to see whether or not it's going to be the lowercase m or the uppercase m. And honestly, it doesn't matter so much to distinguish between these two, just so that you know that these are two separate sides. That's why they're distinguishing different here in your formulas, a lowercase and an uppercase, to let you know that it's catching each end of the rectangle and creating two completely different rectangle heights. Okay, so whenever we are doing our right endpoint, we are going to end up taking whatever it is our starting value is. So in this case, we're starting at an A, and then we are going to add to it an I times then whatever our delta X ends up being. So it's going to be the distance between these two divided by the number of rectangles. That's my delta X. That times the I as I go through here and start doing my sums. When I plug in a 1, that'll hit the first one, and then the next one, and then the next one, all the way through as I'm scooting along from rectangle to rectangle. But I need to start with this A to start here so that it doesn't start at 0 and then go that width over. I need to be sure that I start at A and then go that width over. So that's how we're finding for our right. For our left endpoints, for the left endpoints, we are wanting to actually start at this value of A. But remember, when we plug in our A sub I, it's going to end up putting us to the right. And in order to get back to the left, that's where we did that I minus 1 yesterday. So we're going to see that incorporated here. So again, though, we need to start with whatever that first value of X is. Then instead of just an I, we're going to go and do the I minus 1 to get us to go back to the left side instead of the right side of the rectangle. And then again, it's going to be times my delta X. So it is going to be this portion here for our right and left endpoints that we're going to use when we're evaluating and plugging in to find our heights. And then our delta x here, we're going to use this formula, b minus a over n, to figure out the width of each of our rectangles. Because what we're going to be doing now with this lower and upper sum is we're going to end up coming up with some kind of equation for these guys where we don't necessarily have to have the exact number of rectangles in order to do this. We're going to create a formula so that we could plug in any number of rectangles we wanted to figure out what the area is going to be for each of these. So for example 3 here, it says that we're supposed to find the upper and lower sums for the region bounded by the graph of f of x equals x squared and the x-axis between x equals 0 and 2. So for this problem, the first thing that we're going to need to do is we need to come in here and draw a quick little sketch of what this is going to look like so we can have an idea of what we're working with, where we've got our upper sums, where we have our lower sums, and so forth. So I'm going to go ahead and label 1, 2, 3, 4, 5, 6, 7, 8, 9. That way I can do 1, 2, and 3, because 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So we're finding the area under this curve. We are only finding the area bounded by, it said, the curve along with the x-axis and from 0 to 2. So we're only looking for this portion here. Now, if we were to go in and draw in, let's say we just stick in 3 rectangles. If I divide here, if I did the circumscribed, I would be using these points here to create rectangles that are larger. And if I wanted to do the inscribed, I would be using the left endpoints, creating these little rectangles here. So I'm going to, before we start doing anything else on this problem, go ahead and make a note so that I know on here my left endpoints when I use the left endpoints, that's creating the little rectangles. So that's going to be my lower sum. When I use and do the right endpoints, on the right side, that's creating the larger rectangles. So that's going to be my upper sum. And I can also figure out right here my delta x. I'm going from 0 to 2. So you need to take 2 minus 0 and then divide it by how many rectangles. Now, just for visualization purposes, I put in 3, but we're going to use n for n number of rectangles. So that ends up making my delta x just a 2 over n. So now I'm going to go and create some formulas here for my right endpoints and my left endpoints using my delta x 2 over n here, as well as here, these formulas that we had for our right and left endpoints. So I'm going to start here with my right endpoints. So right endpoints. We said down here that the right endpoints are creating my upper sum. So I'm dealing with the large m sub I. And the formula here to find my right endpoints, it says you have to take your starting value, which for us we're starting at 0. So 0 plus, it's going to be an I. And then times the delta x, and we found our delta x to be a 2 over n. So times 2 over n. And then if I simplify here, that 0 is not going to do anything to it. If I take the I up here on the inside with it, it's just going to be a 2i over n. Now then for my left endpoints, Here, if we follow the formula up here, it says our left endpoints are the ones that are taking it back. So we're going to have this I minus 1. And if we look over here, we said that our left endpoints are creating the lower sum, so that's going to be our lowercase m sub I. So lowercase m sub I equals, and now if we follow the formula up here for our left endpoints, I'm looking at A, which again on this one is 0, plus I minus 1 times my delta x, and remember we figured delta x is a 2 over n. So I'm going to go ahead and distribute, and we can think of this here then as a 2 distributing to the I and the minus 1 to make a 2I minus 2 over n. So I've identified my capital M sub I and my lowercase m sub I, and now I'm going to use these in these upper and lower sum formulas that we have at the top of the page. So let's go ahead and start with the upper sum and see what happens. So our upper sum is the capital S sub n. The formula says that we are supposed to take the summation from I equals 1 to n of f evaluated at capital M sub I times delta x. And for us in this problem, that's going to make it look like the summation from I equals 1 to n. Our f of x is an x squared, so I'm plugging my capital M sub I into x squared, and my capital M sub I is this 2I over n. So I need to plug in and take 2I over n, square it, and then I'm going to multiply it by my delta x, and the delta x is just a 2 over n. And now we're going to work with this summation, do all of our simplifying and plugging in with our summation formulas so that we end up with just a formula with n's in it. So this then is going to equal the summation from I equals 1 to n. If I go and square this term, square the 2 makes a 4, and an I squared, square the n to make an n squared. So it's 4I squared over n squared. And then I still have this times 2 over n, which I can then take and multiply these two pieces together to turn it into the summation from I equals 1 to n. And I'm also in the process of multiplying these two things together. I'm going to separate and pull away the I squared, because at this point, everything else would be a constant. Now, the n is going to be different depending on how many rectangles we choose, but once you choose the number of rectangles, there's nothing more that you're going to have to end up doing to that n other than just straight plugging in. So that represents a constant. So the 4 times the 2 is going to make an 8. The n squared times the n in the bottom is going to make an n cubed on the bottom. And then I have this I squared term. Now what I'm going to do is I'm going to, in one step, go ahead and pull this 8 over n cubed outside of the summation because it's just a constant. And I'm going to take this I squared and I'm going to make the substitution for it that we had on our formula sheet that last go around, which, if I can find it real quick, here are those different formulas. Our I squared broke down into the n squared times the n minus 1 times the 2n minus 1 all over 6. So this is 8 over n cubed times, and this I squared is an n, times an n plus 1 times a 2n plus 1 all over 6. And now it is this here that we're going to go through and start multiplying and simplifying and all of that. Now, before I start multiplying this stuff here, notice that I have an n on the top and 3 n's on the bottom. I can reduce here to make that an n squared on the bottom. And my 8 and my 6 will reduce to a 4 and a 3. So that's going to help us along the way with some of our multiplying and distributing things out by eliminating that extra n. So this is going to equal, I'm going to leave the 4 and the n squared on the outside. So 4 over n squared. And then now inside here, if I start distributing these binomials, an n times a 2n is a 2n squared. Here an n times a 1 is an n. A 1 times a 2n is a 2n. And an n and a 2n together are going to make a 3n. And a 1 times a 1 is a 1. All over that 3. Now I'm going to take and distribute this 4 over n squared while at the same time breaking this apart into separate terms. So this first one's like a 2n squared over 3 times the 4n squared. And I'm not going to worry about reducing anything just yet. So the 4 times the 2n squared makes an 8n squared. And on the bottom, the n squared times the 3 makes a 3n squared. The next term, 4 times the 3n is going to make a 12n. And the 3 times the n squared is going to make a 3n squared. And then here, the 4 times the 1 is going to make a 4. And the 3 times the n squared makes a 3n squared. Now I'm going to go through and I'm going to simplify what I can. And I'm going to end up with the n squareds canceling here to leave an 8/3. Here, one of the n's are going to cancel to leave a 12 over 3n. And here, nothing cancels, so I just have a plus 4 over 3n squared. So now I can choose whatever number of rectangles I want, plug it into here, and that's going to tell me what the sum of my upper sum is going to end up being. So this is my over guesstimate. All right, next we are going to do the lower sum. So if I come in here, my lower sum is my small s sub n. The formula for that was the summation from I equals 1 to n of f of a lowercase m sub I times delta x. We have right here that our lowercase m sub I is this 2i minus 2 over n. So that's going to be what we're plugging into our function, and our function is this x squared. So this is going to look like the summation from I equals 1 to n. Here, if I plug in, it's going to be a 2i minus 2 over n quantity squared times my delta x, and my delta x is this 2 over n. Then what I'm going to do with this one, and actually I had distributed this too, but I'm actually going to go and take it out, because what's going to end up happening is if I take this 2 back out again, I could actually leave this term here as a summation of I equals 1 to n. I can break this apart and leave it as my I minus 1 and let it be squared. And then if I take the 2 and the n out, I'm going to end up with a 2 over n squared times then the 2 over n that I have for my width. So essentially what happens is I'm actually, instead of putting it and multiplying it in, I'm going all the way back to this step. Because remember, we did say that this 2 over n is just a constant, so it's okay to let it stay a constant and pull out. So what's going to happen then here with this is we're going to equal the summation from I equals 1 to n. This 2n, or 2 over n quantity squared is going to make a 4 over n squared. This 2 over n is going to multiply, and it's going to turn into an 8n cubed, right? 8 over n cubed, sorry. And then I'm going to have this I minus 1 quantity squared. That we're going to need to go through and do the distributing. So if I had 2 of these and I multiplied them out, an I times an I makes an I squared, and I times a minus 1 is a negative I, and then I'm going to have another I times a negative 1 to make another negative I to make a negative 2I. And then the negative 1 times the negative 1 is going to make a 1. I'm going to be able to take this 8 over n cubed outside of the sum because it's nothing more than a constant. And now I'm going to be able to use my summation formulas from the other day to substitute for my I squared, my I, and my constant. So my 8 over n cubed came out. Here my I squared, just a reminder, I squared is n times n plus 1 times 2n plus 1 all over 6. So n times n plus 1 times 2n plus 1 all over 6. Then I have a minus 2I, and that 2 can just multiply by what I is. I is n times n plus 1 all over 2. So 2 times n times n plus 1 all over 2. And then this plus I is your constant rule, so it just becomes a plus 1 times n, or plus n. Then we're going to come in and do a little bit of simplifying like we did before. Here, this 2 and this 2 will multiply, or cancel. One's on top, one's on bottom, so we can get rid of them. And I'm going to go ahead, and as I am working some things out, I'm going to go ahead and start distributing this 8 over n cubed to everything as I multiply. Now, when I multiply it to this first one, the n and the n cubed are going to reduce like they did before. So that n is going to be gone, and that's going to become an n squared. Here, the 8 and the 6 will reduce like they did on the other problem, leaving a 4 and a 3. So this is going to reduce to a 3. That's going to become a 4 over n squared. So this is going to be a 4 over n squared. And now all of this here is going to be an n times a 2n to make a 2n squared. This is going to be an n times 1 is n. 1 times 2n is 2n. Add together to make a 3n. And 1 times 1 is 1. All over 3. And now the next term here. When I distribute this 8n, the n from down here, one of them will cancel with the n that is here. So really, this becomes an 8 over n squared. And it is a minus 8 over n squared. And then times this n plus 1. And I'll go ahead and put it over a 1. That way we've got fractions, multiplying fractions here, and it gets a little easier when we start distributing here. And then this last one, if I take this 8 over n cubed and I multiply it to this n will cancel with one of these, leaving just an 8 over n squared. Next thing I'm going to do is I'm going to go ahead and distribute and break all of these terms up. So this is going to be a 2n squared over 3, and I'm going to multiply by the 4 over n squared. So the 4 and the 2 makes an 8. So it's an 8n squared. Here, the 3 and the n squared multiply to make a 3n squared. Here, that's going to be a 3 over 3, and then the 4 over n squared. So when I multiply the 4 times the 3n is going to make a 12n, and then over a 3n squared. When I distribute here, that's going to be like a 1 over 3. If I multiply by the 4 over n squared, the 4 times the 1 makes a 4. And on the bottom, you have a 3n squared. Here, I'm going to distribute this negative 8 over n squared to the n and to the 1. So that's going to be a negative 8 times n makes a negative 8n. N squared times the 1 on the bottom is just over n squared. Here, the negative 8 times the 1 is just going to make a negative 8. The n squared times the 1 makes an n squared. And then I have this plus 8 over n squared. These last two terms are the same, and they're going to cancel. These two terms are like terms, so I'm going to be able to combine those. And I'm going to be able to do some reducing here within these fractions. So if I come in first and I start reducing within the fractions, I have an n squared over an n squared. Those are going to cancel. And I'm just going to get this 8 over 3. Then here, this n and one of these n squareds are going to cancel. Here I've got 12 over 3n. I'm going to cancel an n here to make that 8 over n. So 12 over 3n minus 8 over n is, when we find common denominators, is actually going to give me a, let's see. Actually, let me grab my calculator real quick, make sure I didn't mess something up. Okay, number crunching here with our common denominators. That's going to end up giving us a 4 over n. Oh, if I can find my right color here. And then this last one here, I have a plus 4 over 3n squared. Oh, and scratch that real quick. This plus 4n actually is supposed to be a minus 4n. Sorry about that. Fix that real quick. So what we've found with these two problems is that we have come up then with two equations so that we can find an upper sum and a lower sum for however many rectangles it is that someone wants to put in this parabola from 0 to 2. This is going to be the formula that's going to give us our upper sums. This is going to be the formula that's going to end up giving us our lower sums. So if somebody said draw 10 rectangles, all you got to do is plug in a 10, run with your numbers, and see what you get. Somebody else comes in and says, okay, we'll try doing it if you put 100 rectangles in there. All you got to do is plug in n equals 100 and run the numbers. And you guys are on page 299 now for homework. You should be able to do these last two problems, 31 and 33, now that we've done these lower and upper sums. So on these problems, they actually are going to have you figure these out, and then they want you to go through, and they've on some of them actually drawn in the rectangle. So you just count them, and that tells you how many you're supposed to plug in for your n. And on another one, it tells you what the width is supposed to be of each rectangle. So you can go in then, based on the width, figure out how many rectangles it is would fit in that space. So it's just two problems. I know it is quite a bit. The thing is this stuff is quote unquote hard because of all the work. There's so many different places that you can make mistakes that you have to be really careful with all of your algebra and all of your distributing. But it is very important that you do go through this and actually reduce everything and don't just stop like we did on the previous lesson where we stopped here and just went ahead and plugged in our number, because the next time we come together and we do the last part of this lesson 2, we're going to need to get all the way down to here because we're going to do something special with this here to help us get an even more accurate area underneath the curve.